Hello chemists, this is Miss Placino and you are watching Screencast 12.6 on Titrations and Indicators. In the previous lesson we talked about neutralization reactions, a little bit more specifically Arrhenius acid-base neutralization reactions. It turns out in the lab we perform these type of neutralizations a lot using a technique called titration, and we're going to have to use a group of chemicals that are called indicators. So in today's lesson we're going to talk about how we can determine experimentally, in other words, how we can figure it out in the lab when a solution has been neutralized. Just to review, an acid plus a base are going to yield a salt and water. This is very typical of an Arrhenius acid-base neutralization. The neutralization itself is actually the H plus of the acid reacting with the OH minus of the base to produce liquid water, and then the cation from the base and the anion from the acid will produce the salts. Remember, when we're saying salt in this case, we don't always mean sodium chloride. We're talking about an ionic compound in general. So the identity of the salt really depends on which acid and base were used to neutralize each other. So we're going to be talking about these types of reactions very specifically, these double replacement reactions that always take on the same format for neutralization. When we're in the lab and we perform a neutralization reaction, we usually don't just take a beaker full of acid, a beaker full of base, and mix them together and call it a day. We do something called a titration, and a titration is a very specific laboratory technique where you use a thin, skinny piece of glassware called a burette, and you deliver a very specific volume of solution into your unknown acid or base. And we're going to be doing this in the lab. So this is the technique that we use to determine the concentration of an unknown acid or base. Essentially what we do is we take a solution that we don't know the concentration of, whether it's an acid or base. Let's say for the sake of argument, we've got a bottle labeled HCl in the lab, but we don't know its concentration. This is kind of dangerous. It could be something, not very harmful at all at 0.0001 molar, or it could be 12 molar HCl, which is extremely concentrated and dangerous. So we want to figure out its concentration using a neutralization reaction. So we measure out a volume and we stick it in an Erlenmeyer flask. We add what's called an indicator. We'll talk more about those in a moment. And then we're going to take our burette, which is like this very long, skinny tube with very specific, precise volume markings on it. We're going to take a base that we know the concentration of, and we're going to add it in a very controlled manner. By doing it this way, if we know the concentration of our base, and we know the volume of the base that was added, and we know the volume of the acid, we can figure out its concentration. So this is a really useful technique, and again, we'll be going into the lab and getting a chance to try this out firsthand. When we are performing a titration, we're trying to reach what's called the equivalence point. And the equivalence point is probably what you'd expect it to be. It's the point in the neutralization reaction or the titration where the concentration of H plus and OH minus ions are equal. Hopefully that makes sense. With the equivalence point, you've got these two quantities equal to one another, H plus of the acid, OH minus of the base. And a lot of people make the assumption that at the equivalence point, the pH will be 7. However, this is not always the case. You really need to look at the strength of the acid and the base. And I like to kind of picture the acid and the base arm wrestling each other. Whichever is stronger is going to get its way. So for example, if I'm taking hydrochloric acid, a strong acid, and I'm neutralizing it with, let's go with sodium hydroxide, a strong base. I've got two strong substances arm wrestling each other. No one's going to win that arm wrestling match. It's going to be a stalemate. So in that case, I will see a pH equal to 7. However, if hydrochloric acid is taking on a weak acid, like let's say ammonia, NH3, ammonia is going to lose that arm wrestling match, and the HCl is going to get its way, and I'll end up with, even at the equivalence point where H plus and OH minus concentrations are equal, a pH that is less than 7. Now the reasons for this are definitely more complicated than the arm wrestling of acids and bases, but I don't really want to get into it at this course. It has to do with conjugate acid-base pairs. It can get confusing, so let's just suffice it to say that we're going to talk about it in terms of arm wrestling in this class, and we'll let AP Chemistry go into a little bit more detail. All right. In order to find the equivalence point of a titration or of a neutralization, I need to use something called an indicator. Usually your acids and bases are just clear solutions, and when you mix them together, you get yet another clear solution. So we need to add an indicator. So in this case, in the picture, we have a solution that is clear, and we have a solution that is pink. This is due to an indicator known as phenolphthalein. Phenolphthalein is clear in acidic solutions, and it turns pink in basic solutions. So indicators are often just weak acids or bases themselves, and as that hydrogen ion is either coming off or being added, the Bronsted-Lowry acids and bases, that molecule can change color. So we'll take an indicator like a phenolphthalein, or litmus is another indicator that you're probably familiar with. We'll add a couple drops of that indicator into our unknown acid or base, and then we add the substance we're using to neutralize until we see a color change. So this is what we use to determine when the equivalence point has been reached. Technically, when your indicator changes color, we call that the endpoint. The equivalence point and the endpoint should match up in the same pH range. I'm not going to try to trip you up on equivalence point versus endpoint. I myself tend to use them a little bit interchangeably, but technically, equivalence point is when H plus and OH minus concentrations are equal, and endpoint is when the indicator changes colors. We're going to treat them as though they're essentially the same, because if you've done a good job picking out the right indicator, they should really coincide. They should be at the same pH range. All right, let's get into it. So a little bit more about indicators. You have a list of them on table M. So check your reference table. You're going to see this. There are more than 6 indicators out there, but New York State has picked these 6. The way this table works is it tells you the approximate pH range for the color change, and then what color change occurs. So if we take a look at methyl orange, at 3.1 and lower, methyl orange is going to be red. Once the pH is above 4.4, the solution is going to be yellow in color because the indicator has changed colors. You might be wondering, well, what's going on in that 3.1 to 4.4 pH range? That's where the indicator is changing color. And in the case of methyl orange, it's very likely that it's going to be orange at this point. So usually what we would do is we'd add our methyl orange or any indicator to our solution, and we'd wait for the color to change. We'd want it to go from red to yellow. Just to do another one, thymol blue is yellow at 8 or lower as a pH. Once the pH is over 9.6, it turns blue. In between, it's probably greenish in color. So that's how this table works. And when you go to do a titration, you can't just take any indicator and use it. You're not going to get very good results that way. There's a little bit more to it. So when it comes to choosing an indicator, you have to have an idea of what the pH of the equivalence point will be. Do you have a strong acid arm wrestling a weak base? In that case, you're going to see an acidic endpoint and a low pH. Indicator that changes colors in a low or acidic pH range would be needed. If you've got a strong base arm wrestling a weak acid, you need an indicator that changes color at a higher pH, somewhere in the basic range. And if you've got 2 evenly matched acids and bases arm wrestling each other, you're not going to have a winner, so you need an indicator that changes colors at a pH of around 7. So choosing an indicator is really all about understanding the strength of the acid and bases and anticipating whether the endpoint or the equivalence point is going to be acidic, basic, or neutral. So let's take a look at some titration curves. Here's an example of one with a neutral equivalence point. So before we get into exactly how this neutral equivalence point is produced, I want to talk a little bit about the plots. So along the x-axis, we have the volume of the base being added, and the y-axis, we have pH. So we start at a low pH, so it sounds or looks like we have an acid initially, and then we're going to add base. You can add it a couple of drops at a time, a couple milliliters at a time. Regardless, we're steadily adding base. And if you're to monitor the pH, as you're adding base, initially you're not going to really see much of a change. It's going to start creeping up gradually. And then you get to a point in the curve, on the inflection point, where you have a really small change in the volume of the base that's being added, but you see a massive change in pH. Right at the middle of this curve, the inflection point, is what we call the equivalence point. So here's the place where the H plus ion concentration is equal to the OH minus ion concentration. And in this example, the pH happens to be equal to 7. So if we have a neutral equivalence point, this has resulted because you have a strong acid being neutralized with a strong base. The pH at the equivalent point is going to be equal to 7. Again, go back to arm wrestling terms. You have a strong acid and a strong base. You're not going to have a winner. Neither the acid nor the base is going to get its way. So you will have a pH that is neutral. If you take a look back at Table M, where you have the different indicators listed, you can't just take any indicator and add it to your Owen-Meyer flask. You want to make the right choice. There are 2 indicators from Table M that would fit the bill because they change color around 7. So if you take a look at that graph, I shouldn't say graph, you take a look at that table, you'll see that both litmus and bromthiamyl blue change colors across 7. Bromthiamyl blue is probably a better choice for a titration because it has a much narrower range. If you look, litmus, it's like a 4-unit change in pH. Bromthiamyl blue, I think it's less than 2. So litmus, technically you could use it, but you're going to get better results from bromthiamyl blue. Let's look at an acidic equivalence point. In this case, when the H plus and OH minus concentrations are equal, we see a pH less than 7. So based on what we've talked about so far, hopefully you're concluding that this must have been a strong acid neutralized with a weak base. That's how we end up with a pH less than 7. So whether it's going to be a pH of 6 or a pH of 1, you can't really make that guess with the information you've got, but you know that if it's a strong acid and a weak base, the endpoint will definitely be acidic. Using Table M, the 2 indicators that would be appropriate for this type of titration are methyl orange or bromcressyl green. Both of them are equally good with those narrow ranges where they're going to change color. If we have a basic equivalence point, that means that we took a weak acid and we neutralized it with a strong base. The pH at the equivalence point will be greater than 7. Again, exactly what the pH is. We're not really going to be able to make a judgment call on that at this point in time, but we do know that it will be above 7. The 2 indicators that we could use based on Table M are phenolphthalein or thymyl blue. Phenolphthalein is a really, really common one to use at this level of chemistry. It's got a nice color change from clear to pink, so it's pretty easy for most people to pick up. If we titrate a weak acid and a weak base, this is the type of titration curve we get. Hopefully, as you take a look at that graph compared to the other 3 that we've looked at, you notice that you don't see that big inflection point. In other words, you don't have that gigantic change in pH occurring when a small volume of base is added. We never titrate weak acids and weak bases because the change in pH is way too small to be useful. So if you were just to find a labeled bottle in a lab and it just said acid, you don't know if that's a strong acid, a weak acid, you don't know its concentration, you wouldn't want to titrate it against a weak base like ammonia because you're not going to get a good change in pH, so it's going to be really tough to figure anything out. So you do want to take a strong base like a potassium hydroxide to do the titration. So we never ever titrate this combination of chemicals, not because it's dangerous or anything like that, but just because it's not very useful. Okay, so that really covers the theory of different titrations and neutralization reactions and how we would use the indicators. Now I want to kind of switch gears and talk about the calculation that's going to go along with these neutralization reactions. We're always trying to figure out, or usually trying to figure out, I should say, the molarity of the acid or the base that's being used. We're going to need to know the volume of the acids and the bases. The volume can either be in milliliters or liters, just please be consistent. And we also have to know the number of hydrogen ions produced by the acid, or the number of, and the number of hydroxide ions produced by the base. It says use the subscript. We'll talk more about that in just a minute. This is the formula we're going to use. If you check your reference table, New York State has provided you with a really similar formula, minus the H plus and OH minus. This makes it a little bit more advanced and kicks up the difficulty level. We'll definitely need the H pluses and the OH minuses for the type of calculations we're going to do. So just to make sure we're all on the same page, MA and MB are the molarity of the acid and the base respectively. VA and VB. That's talking about the volume of the acid and base being used. Again, milliliters or liters are fine. I'd say most cases it's going to be expressed in milliliters. Just leave it so that you're not making careless mistakes converting. And then finally, the part that's a little bit tricky is trying to figure out the number of H plus ions produced by the acid and the number of OH minus ions produced by the base. So let's go ahead and try a practice problem. Okay, so we've got this. We're told that it takes 10 milliliters of a barium hydroxide solution to neutralize 18.2 milliliters of hydrochloric acid, 1.5 molar hydrochloric acid. And we're going to try to find the molarity of the base. So questions like this are great. I really like them because there are so many pieces of information I can ask you to figure out. So let's talk about the reaction itself. Formula of the acid. We've got hydrochloric acid. Hopefully we're really familiar with hydrochloric. We know that's just HCl. Barium hydroxide, Ba, OH2. Barium is a group 2 metal, so it has a +2 charge. When an acid and a base react, we know that one product will always be water. And the formula of the salt, well, that's going to be the Cl- ion from hydrochloric acid, and the Ba2 plus ion from barium hydroxide. We'll use the crisscross method. We come up with BaCl2. Write and balance the equation. All right, we've done all the hard stuff. We just have to balance HCl plus BaOH2. We're going to produce water plus barium chloride. I have 2 chlorides on the product side. Now I also have 2 on the reactants. I see 4, so 2 plus 2, 4 hydrogens. Let's put a coefficient of 2 in front of water to get those balanced. All right, so hopefully this is all review of stuff that we talked about in the previous lesson. When we go to perform any calculations, as I said in the previous slide, we have to know the value of H plus and OH minus, and these come from the subscripts. I'm just going to write that again. That's where a lot of people make mistakes. I'm going to look at my formula for HCl. I'm going to look at the subscript of hydrogen. There is none, so that's implied that that's just a 1. I'm going to look at the subscript of the hydroxide for the base. I see a 2, so the value of OH minus is 2. One common mistake that people make is looking at the balanced chemical equations, and they see 2 hydroxides and 2 hydrogens, and they erroneously think the value of H is 2. Don't do that. You need to look at the subscripts. It's telling you how many hydrogen ions are produced by that acid, not the coefficients from the balanced equation. So we're going to use the formula H plus MAVA equals OH minus MBVB. We're going to start plugging in. So I know the value of H plus is 1. I know the molarity of the acid is 1.50 molar, and that I used 18.2 milliliters of it. I know the number of hydroxide ions is 2. I don't know the molarity of the base. That's what I'm trying to figure out. And I know that it is 10.0 milliliters of base that was being used. So now I'm able to calculate MB. So if you take out your calculator, you punch the numbers in the right order, you should come up with a molarity of about 1.37 molar. Make sure that you're including the units after the number. Remember, on this side of the equal sign, M sub B is just a variable. That might as well be X. And the letter M after 1.37 is telling me molar. Okay, so a little bit more theory. This is about the titration itself. Is the acid strong or weak? HCl, by now we have to know our 7 strong acids. That is a strong acid. What makes something a strong acid? It dissociates completely. Is the base strong or weak? Again, you've got to know your 7 strong bases. Barium hydroxide is a strong base. For exactly the same reason, it dissociates completely. So I've got a strong acid being neutralized with a strong base. Is that going to give us an equivalence point or endpoint that is going to be acidic, basic, or neutral? This is going to be neutral. based on what we just talked about. We have strong acid plus strong base. We'll let that suffice as an explanation. And finally, which indicator should be used? Well, we need one that changes in a neutral pH range. So again, based on table M, that could either be litmus or bromthiamyl blue. I'm going to use bromthiamyl blue because it changes colors at a neutral pH. And since a strong acid plus a strong base will give me a neutral equivalence point, I need to choose an indicator that will change colors at a neutral range. So it should be one color as an acid, one color as a base. All right, so that kind of wraps up all the different questions I can ask you based on a titration or neutralization reaction. Make sure that you're practicing with this. Lucky for you, I gave you tons of places to practice on the next page. And go through and remind yourself things about the strength of acids and bases, and then just being able to practice with this formula. All right, that really wraps it up for today. Thank you for tuning in, and I hope you found this lesson helpful.